Kanbarthu. Okay. Okay, this topic starts with a state derivative feedback control for a boost converter through a linear matrix inequalities. Let us see the topics which we are going to cover through the slides. There are nothing about introductions and the descriptions and how the state space model works and the graphical representation. Let us see what first slide through introduction. It is this straight derivative feedback is mainly used to convert this DC to DC booster converter, and this duty ratio is used for to check this less fluctuations in output voltage and current even. And whereas the desired response can be converted for this universal controllers, and the system will be feasible. We can also check the system availability also. If the loops are, if we want any loops to decide their desired locations, we could see their eigenvalues as 0. And the further on slides will be handed over by Gautam.
Yeah, description of the circuit. Circuit is shown and it consists of two capacitors, two inductors, and three diodes, and one active switch. When the switch is closed, the diode D2 is in the forward bias, where D1 and D3 operates in the reverse bias. L1 charged by the input voltage, that is the capacitor 1. When switch is open, D2 is in reverse bias, and D2 works in the reverse bias with D1 and D3 works in the forward bias. Here the capacitors C1 and C2 starts charging. This converter is operated in continuous conduction mode. The conversion ratio is given by the output as the ratio of output and input voltage, and it is given by 1 minus D whole square, where D is the duty ratio. It is the ratio of T on by T off. Similarly, switching period is given by TC. It is a sum of time during the off and time during the on of the switch, and the time. The next slide. Here the equations are given as x is equal to ax plus bu, and y is equal to cx plus du are free space equations, where A is the system matrix, B is input matrix, C is output matrix, D is feed forward gain matrix, Y is output of the system, U is the control input, and X represents the states of the system. And the matrix will be always in the form shown in the slide, that is A. Going to the next slide. Here D is the duty ratio. It is steady state. The proper selection of D is always important. Input voltage V in is considered, and it is always fixed. The V in is will act as a disturbance instead of the input. Feedback is used to set the duty ratio of the switches. The input voltage is always considered as fixed, and the input will act as disturbance instead of input. Feedback gain matrix is operated by K, and the proper selection of K is always important. Uh,
Okay. And further on, we could see this and stimulation results and discussions. And you can see both the graphs, which nothing represents about the capacitor voltage, where VC2 is controlled by state derivative feedback. Here, there's both the qualities of matrix Q and R, which is like hit and trial method, where the voltage will show you hit and it goes through a trial method through a different voltage way. Then the second one is it shows it hits in a zero voltage level and it goes through the other level. And let us see what the graphical representations of the second slide. And it is nothing but always the voltage of if something like we could consider the voltage VC2 like voltage capacitor has 60 volt, then a step of 5 voltage is always increased at 0.08 seconds, and the transition always varies here. And you could see in the slide, like if it hits here at a 662 and goes in the state way, and it takes normally of 0.8 seconds with a ratio of 5 volt in the ratio, I mean, in the significant difference. And I'm handing you over through example with Gautam.
Yes, the example of this system, let us consider the active suspension of a car seat, and it is given with other kind of control inputs. The car mass is here MC, and the driver plus seat mass vertical vibrations caused by a street may be partially reduced by this shock observers. Even though the driver still feel some undesirable vibrations, and these vibrations can be reduced by mounting suspension elements on the car seat, damping of the vibrations of these masses, that is MC, which is mass of the car, and MS, the seat mass. This can be increased by changing the control inputs that are U1T and U2T. So finally, the conclusion. The conclusion of this project, that is, the derivative feedback has been designed for a quadratic DC to DC booster converter, and it takes a steady value that is always 0.18 seconds to settle. However, the variations are too small, are always very small. Settling time also can be reduced by using the concept of decay rate. This remains unexplored for future works. Thank you.